Okay, let's get back to slide 12. This slide talking about basis of n-dimensional Euclidean space. First, we'll assume S is a set of vector, n vector, linearly independent vector, form a basis of an n-dimensional Euclidean space. And given a particular x belongs to the En, which is n-dimensional Euclidean space, then x can be represented as linear combinations of vector a1 to an with a specific lambda. And this presentation should be unique. Only one way to represent that. So that means the linear combination of x in the n-dimensional Euclidean space is unique. To prove this, let's formally set up a theory. Let S will be the is the basis of En, okay, E sub n, and also let A prime belongs to E sub n, and define another set S prime is formed by A prime from A2 then An. So we would like to see if the S prime can be another base of n-dimensional Euclidean space, if only if the lambda 1 not equals to 0. Lambda 1 is the representation of A prime using the linear combination of A1 to An. Okay, so A prime, since A prime is also belongs to the n-dimensional Euclidean space, so A prime can be represented as a linear combination of A1 through An in S. Since this is a double arrow, so double side, so that means if S prime is a basis of En, then lambda 1 is not equal to 0. Or if in the presentation of A prime lambda 1 is not 0, then S prime is a basis of En. So we want to prove from both directions. So this is usually we refer as if and only if. Okay, this is a if and only if situation. To prove, first we're trying to do this direction from S prime is a base to conclude lambda 1 is not equal to 0. So let's assume S prime is a basis of n-dimensional Euclidean space. So we also know that A prime belongs to S because S is the base as well. So A prime can be represented as a linear combination from A1 through An with lambda 1 times A1, lambda 2 times A2, all the way to lambda n times An. And this also belongs to the set S. Okay, so we're going to prove this using a so-called contradiction method, which means initially we want to do is A prime is a basis of En, then lambda 1 is not equal to 0. To do a contradiction proof, we need to go backward. We assume lambda 1 equals to 0, then we're going to prove that S prime cannot be a basis. So that's the contradiction way of doing the proof. So if on the contrary, we're assuming lambda 1 equals to 0, if lambda 1 equals to 0 in this expression, so the first term is gone. Okay, so therefore I can move the A prime to the right hand side, and therefore the negative 1 times A prime plus lambda 2 times A2 plus lambda all the way to lambda n times An will be equals to 0 since both sides are equal. So in this case, we will see that we can represent a linear combination using A prime to An, and the coefficient for A prime is not 0. Based on the definition of the previous slide, we can see that if S is linearly independent, which is the basis of E sub n, then if I represent a linear combination from A1 to AN equals to 0, the only chances this can satisfy is all the coefficient equals to 0. So here, apparently not. So therefore, the S prom is not a basis. So that's a contradiction. Once the contradiction reached, then we can conclude lambda 1 has to be not equal to 0. So that's what we can do this for lambda 2 or lambda 3 or lambda 4. So anyone. So we just assuming lambda 1 is not 0. So this is the direction move from left hand side going to conclude the right hand side is true. By doing, if the right hand side is not true, the left hand side is also not true. So this is what we call the contradiction proving method. The next slide, we're going to prove the other direction, which means, if lambda 1 is not equal to 0 in the presentation of A prom using A1 to AN, then S is the basis. So the reverse direction proof, assuming that lambda 1 is not 0, which is the reverse assumption. One must show that mu1 times A prom plus mu2 times A2 plus all the way to mu n times an equals to 0, where must happening the mu1 through mu n's are equal to 0. So that means S prom is a basis of n-dimensional Euclidean space. However, we also know that A prom can be represented as a linear combination of A1, A2, and AN. So we're using this situation to prove if, and then we replace the A prom in this equation, using the linear combination of A1 through AN. All right. So this is one of the trick we use. So here we have mu1 times A prom, and we replace A prom by this. Okay, and the rest of it is the same. Mu2 times A2 all the way to mu n times AN equals to 0, assuming that. So we can multiply them out, break down, expanding this equation, and collect all the terms from A1, A2 through AN. So the next equation will be mu1 times lambda 1 times A1 plus mu1 times lambda 2 plus mu2 times A2 and all the way through the end. But look at the first term. If lambda 1 is not equal to 0, however, mu1 times lambda 1 has to be equal to 0. Of course, mu1 has to be equal to 0 since lambda 1 is not 0. Okay. Once we're proving mu1 equals to 0, so mu1 times lambda 2 plus mu2 has to be equals to 0. So this term is a 0. So mu2, in order to maintain the whole thing is equal to 0, mu2 has to be equal to 0. Okay? Since mu1 times lambda n also is equal to 0, and maintain the whole thing to be equal to 0, mu n has to be equal to 0. So we can prove that all the mu has to be equal to 0. And then we conclude what? S prom is the basis of n-dimensional Euclidean space. All right. So here we're trying to say is if E1, E2, E3 are the three unit vector, E1, E2, and E3 here are the n-dimensional are the basis for three-dimensional space. If I drop E1 and using that, okay, 1, 1, which is representation of E1 and E2, and then we can still using it as a basis if we drop one of them. So we replace one of these to that. Okay, so similar situation like that. Next slide, we're talking about matrices. We've done with the n-dimensional Euclidean space, and we start talking about matrices. Matrices, A, for example, with the m times n dimension, usually we represent as Aij. I represent the row I, J represent the column, and we can present them as a combination of a column vector A1 through AN, and we can also represent it by a row, which is a superscript. The subscripts usually represent the column, and superscript represent the rows. Okay? If we assume A and B are both m by m matrix, and C can be A plus B together, will be in each individual element added together from A matrix to the B matrix. If we want to do a multiplication of A times B, and A has a dimension of m rows, n columns, and B has to have n rows and p columns, and the result C matrix will have m rows and p columns, but the inner dimension has to be agreed. Okay, so m times n, n times p, and the resulting C matrices will be m times p matrix. Element Cij is the inner product of the row I in A times the column J in B. Okay. But however, if we do this, reverse the situation for the scalar B times A, and this is not a valid multiplication, since P and M may not be agreed to each other. Okay. If M equals to P, then the result will be a m by m matrix. But if we don't know m is m is equal to p or not. Oh, sorry. Next is so-called identity matrix. Okay, identity matrix is forming by unique vectors of column of n. So it's only on the diagonal has elements of 1, off diagonal elements are all 0. So we call it identity matrix. Couple property, identity matrix times A matrix equals to A matrix itself. A matrix times identity matrix equals to A matrix as well. Again, this has to be, inner dimension has to be agreed. Okay. Next property is if A equals to A transpose, and we call this A matrix symmetric. If A matrix is equals to the negative of A transpose, and we call this skew symmetric matrix. Next slide, we're talking about partition of matrices. Okay, here we have two matrices. One is A matrix and the other is B matrix. Okay, and if we want to partition the A matrix into 4 parts, the first 2 parts have n1 column. Okay, second 2 part has n2 column, and these part has only m1 rows, and these 2 matrices has m2 rows. So this is m1 rows, n1 column, m1 row, n2 column, and so on and so forth. And B matrix, we just do a horizontal partition, which is n1 and n2 rows, number of rows. Okay, so the column was not partitioned. And then this case, we can perform a so-called matrix multiplication, A times B, since number of column in A matrix and number of row in B matrix are agreed to each other. So if we multiply them together, it will be A11 times B1 plus A12 times B2. The bottom part will be A21 times B1. Oops, sorry. and this part will be A22 times B2 added together. In order to talk about simplex method, we have several basic, we call the elementary row operation, and these are legit to not changing the solution for your linear system. These three major so-called elements of a row operations are using in the simplex tableau pivot option, and we'll talk about this in later on. But first, let's introduce these three major row operations. First is exchanging two rows. Okay, moving one row and the other row, I and J, can exchange. Second, multiply a constant to a particular row. Okay, constant n to a particular row. The third is adding one row to another row. So adding AJ to a particular row, we just multiply it by n times AI. So please notice that I'm using superscript. I and J represent those are the row A and the row J's and row I. Continue on. If we partition an A matrix into two parts called B and N, okay, just happens the B matrix is a square matrix and the N matrix may not be square, okay, so the rest of the column we call it N. And B matrix is a square matrix, and then we can see if the columns of a B matrix are linearly independent, and that means B inverse could exist if only if I can do a B inverse time multiply to the entire matrix by B inverse. So B inverse times B, B inverse times N. Since B inverse times B equals the identity matrix, and then the rest of the part will be B inverse times N. Okay. And A and D matrices, if we can find A times D equals the identity matrix, also D times A equals to identity matrix, which means A and D both are square matrix, which is number of row equals to number of column. We call it square matrix. Then we define D matrix is the inverse of A matrix. And also we say A matrix is non-singular. What does it mean in matrix algebra? We mentioned a matrix is non-singular. Usually it refers the matrix determinants is not zero, and also all the columns of A matrix are linearly independent. So this is what we have. Look at the rectangular matrix by n matrix A. Okay, the row rank of A represents the maximum number of linearly independent rows in A matrix. Okay, since I have m of those, so maximum could be m, but may not be. So column rank of A, which means the maximum number of a linearly independent column in A, so number of column in A matrix N, so maximum possible linearly independent column is N. Okay, the rank of the matrix A usually defined as either the column rank or the row rank. Basically, we call it rank. Okay, actually, the rank of a row rank and the column rank of a matrix should be equal, but should be less than either M and N both. Okay, less than or equal to. But if the equality situation condition satisfied, and we usually call A is full rank. Okay, so if rank equals to M, number of row, the linearly independent row, we call the A is full row rank. Okay, if the rank of the A matrix equals to n, which is the minimum between m and n, and usually we call A matrices full column rank, but they're the same. This slide number 3, part 3 of a partition of matrix, talking about if we do a proper row reduction, and this reduction usually we refer as a so-called reduced echelon form. Reduced echelon form. We'll continue to do the elementary row operation, including, exchanging two rows. Second, multiply a constant to a rows in the matrix. The third elementary operation is multiply a row I and add it to another row called row J. So if we continue to do so, this is called the performing elementary row operation, and we can reach that. The A matrix have upper left corner is identity matrix called I sub k, means this is a k dimensional identity matrix, and the Q on the right hand side are non-zero part of the matrix, and the bottom part could be several rows with all zero back here. And then the rank of A can be proved is k, is based on the dimension of these identity matrix. So this particularly operation is called reduced echelon form by doing Gaussian elimination, or the Gaussian process, or we can refer as a sequence of elementary row operation. And we're going to show you later on a computer and how to use like MATLAB or Python to produce to generate reduced echelon form without doing by hand. And you will need that. You see that come handy in your exam or homework questions. Okay. Next, we'll talk about A is a n by n square matrix. We call it square matrix. A inverse exists if the row number of all the columns are linearly independent. We'll call it A inverse of A exists. Inverse of A exists if the rank of A equals to n and the determinant of A is not equal to 0. Usually determinant of A is not equal to 0. We refer this as non-singular matrix. A is non-singular. So I can perform a sequence of elementary row operation, or go to its reduced echelon form. It can become an identity matrix altogether for a square matrix. Okay, so the determinant of the matrix can be calculated as well using software. We're going to talk about either we can do this with Microsoft Excel, MATLAB, or Python NumPy library. Next, we talk about assuming a matrix, okay, m times n such that A times x equals to b, and usually we refer to this as a linear system, okay, or system of linear equation. The rank of A equals to m, so rows are linearly independent, and we're assuming generally m is less than equals to n, which is the pretty much the other case in linear programming models. You say maybe sometimes in our linear programming formulation, the number of rows, which is number of constraints, can be more than number of variables. And in that case, what we usually do is adding slack variables, surplus variables, or artificial variable to make it m is less than n. So we're adding one slack variable, one surplus variable, or one artificial variable for each one of the constraints. So kind of expanding the number of columns in the A matrix. Okay, assuming the column can be ordered so that the first m columns are in the squared part, and the rest of the columns put it in the n matrix. And then we can luckily find out the B inverse actually exists. Okay, so that means all these columns in B's are linearly independent. Okay, and we call this B matrix is a basic matrix, and the rest of the m columns in M matrix called non-basic matrix. So now we do a basic and non-basic partition, and later on we're going to using this term, so-called basic and non-basic partition. So partition a matrix between B and N, and we also partition our variable based on XB and XN. So variable in X. Okay, separate into B and N, XB and XN. Still equals to the right-hand side of B. I can multiply, expand this out, B times XB, N times XN equals to B. Since we know B is a square matrix and is an invertible, which is an inverse exists, so multiply both sides by B inverse. Okay. So B inverse times B equals identity, and then we can take it out from our formulation. So I have XB, and moving this part to the right-hand side. So XB plus B inverse times N times XN equals to B inverse times B. Then we can calculate the basic solution. We call the basic solution for the basic variable XB equals to B inverse times right-hand side B minus B inverse times N times Xn. And this is what we call it. XB is the so-called particular solution. Xn will be the free variable. So it's basic variable and free variable, or non-basic variable. That's a free variable. Basically what it means, why Xn is a free variable, because Xn, I can set any value to Xn, and then I can calculate corresponding XB. But in linear programming or simplex method, what is more convenient way, we just simply force all the Xn equals to 0. And we call this basic solution. So basic solution in simplex method has a very specific meaning. In a general equation or matrix partition, we do in this form, basically actually Xn can take any value and then can reverse calculate XB. In simplex method, we just force Xn equals to 0. In that situation, we calculate XB. So this term becomes 0 altogether. This term becomes 0 altogether. But B inverse times B is a current solution. And we call this basic solution in simplex method. Next, we'll talk about the convexity of your feasible region. Before we go into more specific in linear programming model, we first introduce a convexity of a set, okay, a region. Look at this definition. If x1 and x2 belongs to n-dimensional Euclidean space and the line segment join x1 and x2, we'll call the L of x1 and x2, basically this, okay, equals to all the point y, and y equals to lambda times x1 plus 1 minus lambda times x2, and the lambda is between 0 and 1. So that's mean it's a convex combination between these 2 points. Okay, and lambda 1 plus 1 minus lambda 1 apparently equal to 0. Okay, so this line segment, if this line segment is inside the entire set of the feasible region, and then this region we call the convex set. If we can find out some of the points within this convex combination of these 2 points are not belongs to this set, and this set we usually refer as non-convex set. Okay, so this is a basic definition of feasible regions in a space or uh, polyhedral, if they are convex or not, in this sense. Finally, to notice, if it's a linear set, it is convex set for sure, because all the data point between x1 and x2 are on this line segment. All right. So here we have a proposition saying S equals to X belongs to a set called S, which is satisfying A times X equals to B, and X is not negative, non-negative, and then S is a convex set. To prove this is fairly easy. Okay, need to prove two part. If I can find out an x1 and x2 belongs to S, okay, if x1 and x2 belong to S, and then we can define a lambda between 0 and 1, and the y, data point y, is equals to lambda 1 times x1 plus 1 minus lambda times x2, which is the convex combination of x1 and x2. Y is the convex combination of x1 and x2. Okay, then we can prove that. See, we need to prove that the y, A times y equals to B. And also, we have to prove y is non-negative again. So we need to check these two parts if y satisfy S as well. So take a look. If we have x1 and x2 belong to the set S, so both of them has to be non-negative. And also, since lambda is between 0 and 1, so it's non-negative also, so y is non-negative in this case. So positive times positive, non-negative times non-negative, non-negative times non-negative. So it is still non-negative. Plug in A times y equals to lambda times A x1 plus 1 minus lambda times A times x2. Okay, so multiply A by this. Okay, we can expand this, actually equals to both right hand side equals this part equals lambda times A times x1 equals to B. So this part A times x2 also equals to B. I can rewrite, replace them by the right hand side of that equation, B, lambda times B plus 1 minus lambda times B is still equals to B. So y satisfy the first equation, ay times A times y equals to B. Also, we can prove that y itself is non-negative. So therefore, we say S is a convex set. So it's very straightforward and basically just substitution method starting from the definition of S, and we just using the definition of a convex, and we starting with the definition of a convex and trying to see if the convex combination between any 2 points belongs to S satisfy all these definitions. That's it. Okay. Two definition discussed right here. Giving a convex set S belongs to n-dimensional Euclidean space, and also an X belongs to S is an extreme point of S if we, for any x1 and x2 belong to S, lambda between 0 and 1, and X can be represented as a convex combination of x1 and x2. Okay, then x1 must equals to x2. So there's no, I cannot find two other point actually his convex combination can represent. Meaning, if I have a point is a corner point or extreme point on this set, then I cannot find two other point, and which is his convex combination, two other different point, and its convex combination equals to this corner point. So this is fairly straightforward definition. Next, we're talking about a so-called hyperplane separation theory, and we define a hyperplane H in n-dimensional Euclidean space is a set of a part called set of x. X belongs to n-dimensional Euclidean space, and p transpose times x equal to k, and p is not equal to 0. What does this mean? The hyperplane in two-dimensional space looks like the red line, and the p is perpendicular to that hyperplane. Okay, so anything p times x equals to k for a specific k value. In this case, k equal to 10, and then 1, 10, and 10, 0, and 0, 10, and which is the p actually is 1, 1 is perpendicular to that. So this is what we call a hyperplane. Based on the definition of a hyperplane, we can define as two so-called half space. One, it belongs to the right-hand side upper right portion of the hyperplane. We call it half space. The other one is lower left part of it. And both of them are convex. Next slide illustrate the concept. Okay. Next slide illustrate the concept. Let me do this. Okay. And this slide saying this is the hyperplane we have. This is the hyperplane we have. Okay, this is the hyperplane we have. And then p is perpendicular to that. So we define the p times x is greater than k will be the upper right corner of the yellow regions. And now we call the half of a space. Okay. The other h1 equals to p times x is less than equals to k, which is the lower left portion of the blue area, and p is not equal to 0. P is what we call the norm vector of that hyperplane. And this is also a three-dimensional illustration of a half space. Okay, this is the first quadrant, and they have a hyperplane cutting through the first quadrant of a three-dimensional space, and the blue area is the half space. And then we have the other one in the lower left. Okay, so this is, we finished this part. We're going to continue this to talking about basic convexity. Let's do this one, and then we move on. Definition of a ray. The ray and direction, we start talking about what is the definition of a ray. A ray basically has a two component. Instead of a direction, ray consists of a starting point, we'll call the vertex of the ray, which is a starting point x naught, and a direction of the ray. So starting with an endpoint with a direction, and that's a ray. And the direction itself may not have a starting point or vertex. So the ray can be defined as y, and the y equals to, starting from this point, x naught, plus mu, u times d. D is the direction. Mu can be any positive, non-negative number. So definition, S is a convex set in n-dimensional Euclidean space. A non-zero vector D is called direction of S if for each x naught, for every single x naught in the set S, the ray starting from that vertex or x naught, and the direction is containing in x. What does this mean? So first we're defining a ray. Look at the lower left corner. So I have a direction D, and then I have a starting point we call the vertex x naught. And a ray is defined from this particular x naught and using that direction D, and that's called a ray. And mu can be any non-negative number. U can be any non-negative number. To prove this definition, S, the set S is convex. Look at the yellow region right here. Here we have two one direction called D, and then x naught is within this set of S, the start vertex, and then x1 plus mu u times d still belongs to the yellow region. This yellow region expands to infinity. And this particular illustration, E1 and E2 is the axis, or the extreme direction, because any direction D can be using as a cone combination of E1 and E2. We're coming up talking about this in a few seconds in the next lecture slide, and talking about how we can prove this, the use of extreme direction. I'm going to conclude this lecture video, and we start a new one next one.